Hello, and nice to meet you in our next lesson where we discuss time memory trade-off and discuss solutions for sorting problems. On the previous videos, we discussed selection sort, bubble sort algorithms that have n-square time complexity and constant memory complexity. At the same time, we have counting sort that can have linear time complexity if we sort some values with small range that is difference between maximum and minimum values. But if this range is very big, then we have huge memory complexity and also time complexity. So we should understand where we should move next. As a next step, we try to decrease time complexity even if we have just comparable objects, not objects from some range. Okay, we suggest a quicksort algorithm. The quicksort algorithm is modification of bubble sort algorithm. As you remember, in bubble sort algorithm, you have the main idea that is local order gives us global order. It means that we compare each pair of two values and check if they're in correct order. We swap them, and after the first pass, we get the maximal value in the end. But why the maximum value should be in the right correct place after the first step? Let's try to put another value in the correct place, and this is the main idea of quicksort. For example, let's put as 5 to the correct place. What does it mean, correct place? It means that all elements from the left of 5 are smaller than 5, and all elements on the right of 5 are bigger than 5. How we do it? In the bubble sort, we have one pointer that moves from the left to right and check with elements that on the next place, and if they are in correct order, then we swap them. Here we use two pointers. The first pointer moves from the left to right, and the second pointer moves from the right to left. And if they find incorrect pairs, then we swap them. What does it mean, incorrect pair? If we look to 5, then incorrect pair here is the following. If we look to element on the left for the left pointer, then incorrect element for here is some element smaller than 5. Because here should be only elements, bigger than 5, because here should be only elements smaller than 5. And for right pointer, the incorrect element is element that is smaller than 5, because here should be only elements bigger than 5. That's why when we find such element, how we do it? We just move the left pointer to the right until it finds element that is bigger than 5. And we move right pointer from the right to left until it finds an element smaller than 5. And when we find it, we just swap them and continue moving our pointers. So here the next pair is this one. We swap them and find the correct order, because when we just our pointers meet here, then we stop this process. So when 5 becomes on the correct place, after that, as it was in bubble sort, we decrease the size of sorting space. But here we can say that all elements on the left are smaller than 5, all elements on the right bigger than 5. That's why we can sort each part, the left part and right part, independently, and after that the array will be sorted. So we do it recursively. We sort left part, right part, and so on. For this idea, we use recursion function that have two borders, left border and right border, for sorting segment, and we try to sort this segment. So we choose element value which one should be on the correct place, but here how to choose this value, it is hard question. For example, it should be some value inside this segment. For example, we choose a value on the middle of segment. So after that, I is left pointer, and it starts from the left border, and j is right pointer, and it starts from the right border, and we continue the process until they meet in some position. So firstly, we move the left pointer until it points some element smaller than m, and it stops when we find element that greater or equal m, and we also move j, the right pointer, we move it to the left until it points element that bigger than m, and finds element less than m, and this pair is incorrect pair, and we swap them and continue. We swap them if and only if I and j are still on different, are still such that I is left on the left of j. If they are meeting, if they meet, then we do nothing. Okay, and after that we can be sure that m on the correct position, and we can be sure that, for example, j is pointed elements, the required element, and we can sort independently left part and right part if these parts are not empty. For sorting wall array, we just put as a left border and right border the leftmost element and rightmost element of our array. But what about the time complexity of this solution? So it is not so easy to understand what is the time complexity. Firstly, let's think that m is about the middle of segment, and we let's think that in the most iterations we have m about around the middle. Then we can say the following idea. So on the first path, on the first pass, pointers I and j are moving from left to right until they meet. So they are passing all the array. It requires linear time. After that, we invoke the left part, and for the same function for left part and right part. And if it is about the middle, then we can say that left part is about n over 2. And the right part size is also about n over 2. And we invoke this one, and we have linear complexity for each part, and the total complexity of these two invocation is n over 2 plus n over 2. Each of them invokes also two QSort for two parts, left and right, and we have size of such parts n over 4 and n over 4. And for this one, n over 4 and n over 4. There are 4 such summats. And so on. Each of them is dividing to 2 parts. And after k phases, we have n over 2 to the k size of elements, size of segment, and there are 2 to the k different segments. So we stop when the size of segment is 1. In that case, it is already sorted. In that case, we don't invoke the left part, right part because of these conditions. And by this definition, by this question, we can find by definition that what is the k. Firstly, before that, let's just collect each part of this sum to n, because here n over 2 and n over 2, 2 summats, n over 4 and so n over 4, 4 summats, and so on. Each of them is sum is n. And we have total complexity nk. So k is such that n over 2 to the k is 1. It means that 2 to the k is n. And by definition, k is log n base 2. So the complexity is n log n. Let me remind you that we can just skip the base of logarithm, because changing the base of logarithm, if it is constant, is just multiplication to constant. That's why we can just write n log n. So, but what happens if m is not in the middle, but in the end or in the beginning of the array? It means that we don't invoke this part, and we have only this part with size n minus 1, then n minus 2, then n minus 3, n minus 4, and so on, and we just sum it, and it is exactly the complexity that we had for bubble sort. That's why complexity will be n squared. So in worst case, if our choice of m is very unlikely, if we have bad luck, then we get complexity n squared. That's why it is important how we choose m. There is different strategy. Maybe you can choose the first element of segment, maybe the last element of segment, because maybe these values are the middle value. But maybe you can choose some middle between lasts and so on. Maybe you can choose something else. But anyway, someone can prepare data for you if he knows your algorithm prepare data such that in these places are the maximum values on the segment, and in that case the complexity will be n squared in worst case. But in if we have some randomly generated data, then in average case we have n log n complexity for real world data. If no one attack your system, but if someone want to attack your system, they can give you this incorrect value that give you get the very slow sorting algorithm, and it can be very bad for your system without some more complex attacks. It can be the so bad attack for this using this data. How can we fix it? For example, we can just randomly choose one element between F to R. In that case, no one can attack you, but with very small probability, we can get some complexity n squared. Okay. What about memory complexity? Where we use here memory, no additional arrays, no just constant variables. Maybe you think that the memory is constant, but it is wrong, because we have recursion, and recursion store all values of local variables, including parameters to stack, system stack, and complexity is number of local variables times depth of recursion. Here, depth of recursion is k, that can be log n in best case and average case, and can be n in worst case. That's why member complex from log n to n. So we have some improvement for our sorting algorithm. This algorithm have n log n complex in average case, best case, but n square in worst case. The same for memory. We pay with memory for improvement of complexity, but in worst case it is still not so good. Bubble sort better than quick sort, we see in worst case. But in average case, quick sort much better than bubble sort and selection sort. But we pay with memory for this improvement. Okay, in next videos we discuss another ideas how to sort your array with n log n time complexity.